In 2019, researchers at the University of Michigan found out that they could use Google Home to open garages, turn on and off the thermostat, and even send messages. So what's so special about this? They didn't use their voice. Instead, by using a specially designed laser that they pointed at the microphone, they were able to trick the Google Home voice assistant into thinking that a human was talking to it. So here we are today, tackling speaker diarization to ensure that my voice assistant doesn't send a message to my mother saying that I hate her. So what is diarization? Fundamentally, it attempts to answer the question of who said what. So with the laser example, we could use diarization to determine whether or not a command is from the owner or from a fake laser voice.
Diarization consists of two main parts. First, making an audio embedding, and then clustering those audio embeddings into different speakers. In our project, we focus on finding a better audio embedding. There's a variety of existing approaches to creating audio embeddings for speaker diarization, for example, I vectors and D vectors, but they often make assumptions about the data distribution that isn't necessarily true. Contrastive learning has successfully been used on other audio tasks like emotion recognition, so maybe we can use it for speaker diarization. Put simply, contrastive learning is the idea of learning a data representation that best distinguishes between similar and dissimilar inputs. We do this by creating different augmentations on the same input, which in our case is audio.
So for this project, we used the Flickr audio caption corpus, which is composed of 40,000 English captions spoken by 183 unique male and female speakers. The data is sampled at 16,000 hertz, and we use an 80-10-10 split. So for our baseline, we decided to try the D-vector approach on an LSTM, where we use the last layer of the LSTM to generate our audio embedding. And even though there's only 183 speakers, we use 500 hidden units in the last layer to create sparsity and make it easier to distinguish the speakers.
For our main approach, to generate contrastive augmentations, we first apply a random time stretch to the audio, then convert them to spectrograms, and finally use well-known image augmentations on the spectrograms, such as random cropping and color jitter. In this way, we're able to generate 6 distinct views for each audio, and the data loader will select 2 at random to put together in a pair, which allows our model to be view invariant. Our model architecture is inspired by Sinclair. We have a CNN encoder, Resident 18, followed by our MLP, and the last linear layer is used as an embedding. One version has ReLU and the other one has softmax. Our loss function uses cosine similarity to maximize agreement of same speaker representations by pushing it to a score of 1, and different speaker pairs to have a score of -1, though in practice it gets close to 0.
After trying out different values for our training loop hyperparameters, we got both our baseline and our contrastive approach to converge in training. So from here, we could use the final layers as embeddings for our clustering.
For clustering, we decided to go with spectral clustering, and we evaluated our results using the diarization error metric, which is a ratio of incorrect classifications over our total audio. Overall, we found that our contrastive method did much better than our LSTM, and softmax did much better than ReLU, likely because the latter is more expressive than the former. Our best model achieved a performance of 0.189. State of the art has DERs of 0.12. This shows that our contrastive softmax approach is promising, because if we use it with a more complex clustering approach, we can probably achieve comparable results.
So there's a bunch of different ways we can improve on this. For example, we can use a more recent self-supervised architecture, further hyperparameter tuning, using an RNN encoder, and doing better clustering. So now what we're going to do is we're going to walk you through a quick demo of our diarization pipeline on an additional test data set.
We will show our diarization pipeline on the JL corpus, which is an additional test dataset of single speaker audios from 4 different people. We have already loaded in 512 examples and did a forward pass through the model to create our embeddings. I randomly picked 4 audios from 2 different speakers, and these are the indexes that correspond to those speakers. I simulated a continuous audio clip by stringing them together in a list. Running our clustering algorithm on this list, we see that the method correctly determines the speaker source for each of the 4 segments, showing that our embeddings are indeed robust. We also computed the DER on the entire JL corpus and found that our DER was 0.263, which is quite reasonable.